Thank you very much. I'm very happy to be here and have the opportunity to give a seminar talk. And I was told that maybe not all of you are very familiar with these subjects that I will talk about. So my talk will include a kind of an introduction into defining the terminology and the things that we study. Okay, what are the things that we study? We study a particular kind of differential equation which is called the canonical system. And it is a differential equation of the following form. Y prime of t is c times j times h of t times y of t, where I will explain in a second what the ingredients are. So where is t? I should be now in this place more specific. I will consider a canonical system on the half line. So let's say on a half line starting from some point A up to infinity. So that equation should hold on that half line. And what are those ingredients? So Z is the spectral parameter, so it is a complex number. And J is just a signature matrix, so it is a 2 by 2 matrix, so I consider a two-dimensional canonical system. And it is such a signature matrix. And I mean, Y, the solution should be a function defined on the half line going to C2 because it's a two-vector equation. And H is the essential ingredients. H is the Hamiltonian. It is called the Hamiltonian. And it is a function which lives also on that half line, goes to R2 times 2, and it should have several properties. Yes? So with the following properties. The function H should belong to the space L1 locally, so on every compact sub-interval of that ray it should be integrable. And not only that, it should be non-negative almost everywhere. And I'll look at, in this talk, at canonical systems where the Hamiltonian behaves nicely at the left endpoint so that we can talk of an initial value problem, and it's not nice at the right endpoint. So what we assume is that the integral from a to a plus some, well, let's say b, of the norm of h is finite. But at the right endpoint that's not the case. So if I start at some b and integrate to infinity, then that should be infinite. B is somewhere on that ray. Of course, by local integrability it doesn't matter where I choose. Yes, one more condition which we include just to make things easier is that the set of all points t where the Hamiltonian vanishes is a zero set. So this we also impose, but that's not an important thing. Now, the topic I want to address today belongs to the spectral theory of such systems. And so maybe I should briefly explain what I mean by spectral theory of such equation. If we talk about spectral theory, what we want to have is the operator, preferably a self-adjoint operator, because then we know what the spectrum is. Yes? So we would like to associate with that equation an operator model. That operator model consists of several ingredients. It consists of a Hilbert space L to H, and that notation is almost self-explanatory. We have a non-negative matrix function, so we can just look at the L2 space of that. So we can look of the well, then the norm of the space is that. Yes, that's the norm of the space. Well, almost. Let me write it like this. Yes. So we can look at the usual L2 space with respect to this matrix valued measure, which is all functions which are measurable and such that this is finite. And that's almost the model space. It's not quite. This model space is a subspace of that usual L2 space. Yes. Okay. That's a Hilbert space. Then the next ingredient is an operator, the maximal operator. So you see, maybe some of you have learned about differential operators already, and you see we follow the usual scheme. We use the coefficients of our equation to define a Hilbert space, and the operator will model the action of the equation. So what is that maximal? It's called the maximal operator. Maximal operator. And well, I want to specify it rather in terms of its graph instead of an action, because, well, also at that point I should say that I will simply ignore quite some exceptional cases, some technicalities and such things. So what I say today, it's not always strictly correct, only sometimes it's only generically correct. Yes, so that I should say. Okay, what is the maximal operator? I specify its graph, and its graph is just all the pairs which are in our space, such that the equation takes place. Yes, so you see that if you imagine for the moment that the Hamiltonian H were invertible, then you could put it on the other side, and then here stands really the action of a map. Yes, F is mapped to JH inverse F prime. In general, you can write it only that way. But never mind. The third ingredient to our operator model is a boundary value map. So this is a map, boundary. It goes from the maximal operator to C2. It's boundary map. And what does it do? It maps a pair in the maximal operator. It simply maps to the evaluation at the initial point of F. Yes? One can show it is well defined and everything. Yes? That's a lemma. Okay, so this is our operator model. What does one show for this thing? A couple of things. I just noted some of them here. So, for example, you show that the boundary map is surjective. You show that the maximal operator is closed. You show that its adjoint is equal to the kernel of the boundary map. In particular, it is contained in T max itself. And then you use this adjoint. You see, it is a symmetric operator. Yeah? It is because making twice the adjoint leads you to the same operator again because it's closed. Yes. So what you get is a minimal operator. The minimal operator, which is defined as the adjoint of the maximal one. And this is a symmetric operator. Symmetric. How does this minimal operator emerge? As you can see here, it emerges by requiring boundary values everything 0. So the maximal operator just corresponds to the equation. The minimal operator corresponds to the equation plus the boundary condition, everything is 0 at the boundary. Okay, so that is our operator model. Now, the situation, we want to make spectral theory, we want to have something self-adjoint. Unfortunately, there is a gap. this symmetric operator, it is contained, the minimal is in the maximal contained, but there is a gap. So the situation that you need, okay. It should be up, or no, how does this work? Like this? No.
No, I think it's not possible to make it lower.
Clever, yes. Okay, so in any case, the situation that you meet is the following. You have the maximal operator here, you have the minimal operator, which is smaller, and I mean, thinking of the nature of our boundary map, it doesn't surprise much that the gap that you have is two-dimensional. And now you have in the middle, you have a one parameter family of self-adjoint operators, which are in between, yes. So here is a one parameter family of such self-adjoint operators. And each two of those self-adjoint operators are one-dimensional perturbations of each other, so the spectral properties will more or less be the same. So we can just pick one and work with that. Okay, now what does the theory further tell us? One can show that this self-adjoint operator has simple spectrum, which means that I find a scalar positive measure, so that's a positive measure on R, scalar, and I find a unitary operator from my Hilbert space to the L2 mu space, such that this unitary operator puts my differential operator into multiplication. So if I make my differential operator and put it there, then I get multiplication operator. Yes? So that's the multiplication operator in that L2 space here. Multiplication by the independent variable. Okay, so having simple spectrum. And now the question arises, of course, this works. Question, it's nice to have a spectral measure. It is, for example, given by the spectral theorem. The spectral theorem tells us it exists. The question is how to find it, or how to find one which does the job. So the question, how to find mu. How to find mu. And there is a method how to find mu that goes back to Hermann Weyl in the 1930s or something. And it's really a very nice geometric argument. How to find these, and it starts from the fundamental solution of the equation. I mean, it's just in the standard way that you show that for every initial value you find a unique solution. Yes, it's just Banach fixed point as always. So now let us start from the fundamental solution matrix. Fundamental solution of the equation. Yeah. Let me call it W. So if you are given a Hamiltonian, what is that? It satisfies the W of H at the initial point should be the identity matrix, and then it should satisfy the equation. I should say here it is very practical in many respects to pass to the transpose. So the equation that I want to be satisfied reads like that: d over dt, W of H, T, and C, J is C, W of H, T, and C, H of T. That should hold almost everywhere on that ray. And as I said, it is a usual argument to show that that exists. So there exists a unique function where absolutely continuous in T, And since the spectral parameter enters so is simply, it is an entire function and satisfies this equation. Now, Weyl's method is based on two properties of this fundamental solution. This fundamental solution has a lot of properties, but two of them are used in Weyl's method. The one is just, as always when considering differential equations which are uniquely solvable, the multiplicativity of the fundamental solution matrix. Yes? So the first ingredient is multiplicativity. I mean, what does it mean? Yes, here you have your array where the equation lives, and then you look at two further points, let's say B and C, and then you solve the equation. You start here and you solve the equation up to there. So this is done by that guy. On the other hand, you start here and you solve the equation until here. This is done by that guy. And how are those two related? Well, you start at that point, solve the equation up to here, which now should be the fundamental solution of the Hamiltonian, but the one that starts at B now. Yes? At that point. And, well, the product of the two is that. So that's just a multiplicativity property, which is a general thing. The second major ingredient is now, specific. It is kind of specific for the equation, and it is the positivity. Yes? So, positivity. In fact, there holds an equation. It looks as follows. I just write it down. It's W of H, B, C, J, W of H, B, W star minus J over C minus W bar is equal to the integral from A to B. So I should say for every B between A and infinity. And here comes some W of H T C H of T W of H T W star dt. That equation is very easily derived from the system. And here the significance of positivity manifests itself, because you look, this matrix being non-negative means that if you put z equal to w, then on the left and the right there is just the same, so that integral will be non-negative. So positivity now means that this thing here is a positive definite Hermitian kernel. This expression. Yes? I mean, you see that this is a Hermitian kernel, because if you switch z and w, just get star of it, and by this equation it is a positive semi-definite one. Yes. Okay, and now we can show this method of Weyl. It is a method of nested disks, which leads us to the spectral measure. Okay. Nested disks. Okay. I mean, you know that whenever you have a 2 by 2 matrix, then you can, an invertible 2 by 2 matrix, then you can make a fractional linear transformation out of this matrix. So I mean actually you have this group action of invertible 2 by 2 matrices on the Riemann sphere by fractional linear transformations. So let's play that game with our fundamental solution matrix. So let me write the fundamental solution matrix in its entries. Let's say W1, 1 of H, T and Z, W1, 2 of H, T and Z, and W2, 1 of H, T and Z, and W2, 2 of H, T and Z. So that's my fundamental solution. And now, how do you make the fractional linear transformation? Some point theta is mapped to yes, that's how you make a fractional linear transformation out of the matrix. So that guy, let me call it phi of HTZ. That's now a fractional linear transformation. And what we are interested in, or what we look at, is the image of the upper half plane, the closed upper half plane, and as I said, I work on the Riemann sphere, so point infinity is included here. So I look at that image that gets a name. It is called the Weyl disk. It's some disk somewhere. Well, somewhere? No. Not just somewhere. Positivity implies that that disk is contained in the upper half plane. That's because of positivity. So you have the picture. So here you have the upper half plane, and then that disk is here somewhere, yeah, omega of HTZ. And now multiplicativity comes into play. Multiplicativity implies that when those you have a family of disks, yeah, for every Z and for every S less than T, it holds that the disk at the time S is the larger one. Yeah, if you grow with T, they shrink. So omega H T Z. So what you get is a nested family of disks. So when you let T grow, yes, then you get a nested family of disks. Well, a nested family of disks, if they shrink to something, to what? Now, well, either to a limit disk or to a limit point. Yeah? And what it does, we can easily determine. Namely, you can estimate the diameter. Yeah? If you look at the diameter of those disks, let's call it omega ht. Well, let me say if Z is on the imaginary axis, and I work on the Riemann sphere, so I take the diameter with respect to the chordal metric. If you look at that, then it's straightforward. Estimate 4 over y times the integral from a to t over the trace of h. Yes? And now you remember what is still here on that blackboard. We have assumed that h is not integrable towards infinity. I mean, h is a non-negative matrix, so the norm is roughly its trace. Yeah, so the trace is not integrable at infinity, so you see that when t goes to infinity, that goes to 0. That goes to infinity, then that goes to 0. So because of that, and that's a if and only if, yes, so because of that, we know that those nested disks, they shrink to a point, and now we can define a function. We can define a function.
Chi.
Yes. Chi is the chordal metric, and if you imagine you have the Riemann sphere, so it is just a ball, yes, then you take 2 points, let's say theta and somewhere psi, and then you take the Euclidean distance. Yes, so I mean this is the sphere in R3, and you just take the Euclidean distance. Yes, so this is a metric. It is at most, if that's the unit ball, unit sphere, then it's at most 2. Yeah. Yeah, that's. And the topology it gives you is just the topology of the one-point compactification of the complex numbers. Yes, the topology. Sorry for the mess here with the water, but okay. Yes, the function, the Weyl coefficient. It's called Weyl coefficient, or the name coefficient is for another reason, but never mind. We define a function as that limit point we obtain there. Yeah? That limit point of these nested disks. Yeah. Well, I mean, an analytic way to write the definition is the following. We just take any point of those disks, yeah, just anything, like here and that one and next one, and whatever we take, the sequence that we obtain, because they shrink, the sequence will go to that one point in the middle there. Yes, so that gives rise to analytic definition. Well, I have two definitions. Well, it is equal to limit t goes to infinity. And now I have my action of the fundamentals of this fractional linear transform. So it's W11. Let me skip the parameter. Well, no, let me not skip the parameters. Theta is something, doesn't matter. Well, some point, because they shrink, it doesn't matter which one you choose. Okay. I mean, I should be careful, because here we established shrinking to a point for z on the imaginary axis only. But that's just a normal family argument. You can just argue with, I think, once applying Vitali's theorem, that this convergence on the imaginary line, just by analyticity, extends to convergence everywhere locally uniformly. For every set in the upper half plane. So like this. Yes, this is just a normality argument. Okay. Well, we wanted to find the spectral measure mu, remember? We started with the self-adjoint operator, and abstractly we know it exists, but we wanted to find one. That function QH here is analytic, and I mean, because of the construction, it maps the upper half plane into itself. Such functions have an integral representation. Actually, I mean, their imaginary part is a Poisson integral, and the function itself is nearly a Cauchy integral. So it looks like that. That's the guy. It does the job. It is a spectral measure. And so we have a unitary operator U from our model space into the space of this particular measure, which may put our differential operator to multiplication. And that unitary operator is an integral operator which you can write down explicitly. Integral operator. Yes, You can write it down explicitly. I mean, one thing maybe, if you think of the simplest possible matrix function h of t, yeah, just let h of t be the identity everywhere. Then this will be just a normal Fourier transform. So one can view that if one wants to, one can view that as a generalization of theory of Fourier transform. Okay, now that was kind of an introduction to the object, and now maybe I would like to come to the scientifically new things. So what do we investigate? If you remember, the title of the talk was High Energy Asymptotics for the Weyl coefficient. What the Weyl coefficient is, we already know. It's this construction with these nested disks, and the significance of the Weyl coefficient is that it gives us the spectral measure. Yes, and now we look at what is high energy asymptotic. So now, how does QH behave towards plus I infinity? So I mean that function, it lives on the upper half plane, so you can just ask, what does Q of Iy do for y large? And this is sometimes some people called high energy asymptotics, for a good reason. I mean, sounds much more impressive. This. So that's what. I mean, why do you want to investigate that? Because just by very classical abelian and Tauberian theorems, it is known that the behavior of QH towards I infinity, because it's a Cauchy integral, corresponds to the behavior of the tails of the measure going to infinity, left and right. Yes. So and that's certainly object of interest. Yes, we want to know. We have the spectral measure. We want to know how fast does the spectral measure grow towards infinity. If you think of a discrete measure, maybe you want to know what is the distribution of the points where it is supported. Such questions. Yes, and this can be translated more or less back and forward to asking for the behavior of the the Cauchy integral towards I infinity. So that's why we want to investigate exactly that. Yes, and then now what we did, I should say who is we. This is a couple of papers together with two friends, Matthias Langer from Glasgow and Raphael Bruckner from Vienna also. So this is a very recent joint work. It's not, well, manuscripts are not yet finished. So let me put it that way. I mean, some are, some not. Okay. Yes. I think Okay. I should say that it is I write that it is an intuition, but it's much more than that, as I hope we will see in 10 minutes or so, that the behavior of the Weyl coefficient for Weyl large, it corresponds to the behavior of the Hamiltonian at the left end point. The initial point, let's say. Yeah, so this is an established intuition, established by several results which are known. And it is much more than an intuition, as I said. And the results that we have are exactly confirming such intuition. So we have 3 of them. So let me say A, B, C. And they deal with different situations. So the first theorem deals with very nicely behaving functions. Yes, so nice Q. In which sense? In the sense that if I move upwards there, then that function will have an asymptotic. So it will have a nice asymptotic, nearly like a power. So Q of Iy should asymptotically be some constant, which for practical reasons I write as I omega, never mind, it's just a constant, times some function f of r, and that function should be regularly varying in sense of Karamata, which means that it's nearly a power. Yeah? It is something really which you can handle nicely. The second theorem we have, it's just for arbitrary Q. So this is just really in the general case. And it doesn't, of course, we don't have asymptotics in general. Yeah? The Q can behave as it likes. But what you get in the general case is you get bounds. You can look at the absolute value of Q. Well, that you can get some function like, called it U, because of upper bound, bounded. Never mind. Okay, what do I mean with the symbols? Sorry. This symbol means that the quotient tends to 1. So that's really exactly like that. This symbol means that the quotient is bounded above and bounded away from 0. Yeah, so you have mutual inequalities with some constants that you don't know, but some constant. Yes. It's larger or equal than the imaginary part, trivially, and this is, again, less or equal with some constant. And here comes some lower bound. The thing is that those ingredients are explicit in terms of age. Yes? And the third theorem now deals with, let's say, wildly behaving Q. I mean, actually it is not it's a theorem, but it's not a theorem. It is a range of examples. Yes, that theorem rather. So if you have a function, then you can look at the set of its limit points. Well, I mean, it is just a set of all limit points when you go up there. So all numbers, let's say, zeta, for example, which you can write as the limit of Q of I y n, n to infinity, where yn is some sequence that goes to infinity. Yeah, so just all limit points that you can get. And the third theorem says that these can be more or less arbitrary. can be anything. I mean, subject to the trivial necessary conditions, but morally it can be anything. So as I said, it's a range of examples. Yes. Now maybe in order to formulate those theorems, I would start with number B, with the second one. Yes. I will start with the second one. It reads as follows. Okay, so we are given a Hamiltonian. And I write that Hamiltonian, it's a non-negative symmetric 2 by 2 matrix. And let's say it lives on the right half line. And as a notation, I use mj for the original functions of the h. So mj of t is supposed to be the integral from 0 to t of hj. And well, okay, then I pick some number, so choose some number gamma which is small enough. So this is not significant, it's just some small number. Yeah? What is significant is I call it t naught of y, let this be the solution of the following equation. So you take the geometric mean of the diagonal entries of the original function. Yes? So I mean, this just means you take the geometric mean, take its inverse function, and plug 1 over y. Forgetting the constants, eh? They are immaterial, they are not important. Yes, so that's an important thing. And then what holds is that we have that equation, that style I wrote down there. So absolute of QH of IY and the imaginary part of QH of IY, and then this is comparable with it's like that, M1 of these over M2 of these. And this is always larger, up to some constants, of course, always, than the same stuff. What is here? M3 squared M1 times M2. Yes? Well, if you look at that, well, there are some things one should observe. The one thing is that those bounds on the left and right side are indeed explicit in H. I mean, up to that one has to invert that function, which of course in concrete cases may be troublesome, but it is still kind of explicit in H. The other thing is that the absolute value is completely determined by the diagonal entries, while the off-diagonal entry just appears in the lower bound and, well, I mean, worsens the lower bound. So having an off-diagonal entry means that you produce a gap between the bounds. One thing is that one should say that, remark maybe, that mostly lim inf of that guy, lim inf of 1 minus this m3 over and so on, yes, is larger than 0, yes. So if you more or less probabilistically pick one Hamiltonian, then you have a good chance that that will be positive and the bounds on the left and the right will be comparable. Yes. Okay. So this is this one theorem. Proof of the theorem is following the construction of the Weyl function. This is one thing that makes it much different from the proof of the theorem A. It is simply possible, just in general, to, I mean, you know, when you have a 2 by 2 matrix and you look at that fractional linear transformation, then you can simply compute the center and the radius of those disks. That's just linear algebra, if at all. And if you do that, you can perform that, which gives you, let's say, the center and the radius, and that gives you, so to say, a square where you know that your Weyl function must be inside. Yes, and then that you can use to obtain estimates. This idea. So the idea is just to, well, kind of balance y, if here is I, to balance y and t so that this geometric estimate gives you a meaningful thing. That's the idea of the proof, and it's possible. Leads to that, which is mostly sharp. So now about the theorem B. Yes, maybe I continue it here. No. That was theorem B. Theorem A, sorry. Theorem A. I will not say anything about theorem C. But about theorem A, I want to say something in 5 minutes. And it reads as follows. Again, let there be given our age as above. And we impose one more normalization. We assume that the trace of h is identically equal to 1. I should put it in brackets, this assumption, because this can always be achieved just by a change of variable in the equation. So it doesn't change anything. It's a normalization. It is actually not an assumption, but only a normalization. And then the following are equivalent. 1. We have such behavior, such nice behavior of Q that you have something regularly varying up to a constant. So there exists f regularly varying at infinity. And there exists some constant such that, well, you have that. I mean, if you want to write it in less sophisticated language, you could just say that the absolute value is regularly varying and the argument has a limit. It's the same. But it's kind of practical to write it like this. So that's the condition on the Weyl function side. The condition on the Hamiltonian side is the following. The diagonal entries m1 and m2 of the original function, I use the same notation as up there. They are both regularly varying at 0, and the off diagonal entry isn't too bad. So the limit delta, which is the limit of m3 of t over that arithmetic mean, yeah, m1, m2, 1/2, of t for t towards 0 exists. That limit exists. And if those hold, then we have an explicit formula that connect the ingredients here with the ingredients there, namely f of y is just what it was up there. And omega, well, long and ugly but explicit. One thing which is interesting to observe is that f, so the behavior of the absolute value, similar as here but only in a much stronger sense, it depends only on the diagonal, while the argument of q, which has a limit, it depends on delta. Yes, it actually does only depend on delta. So you see these different roles of diagonal and off-diagonal entries. You fix the diagonal and let the off-diagonal kind of turn on and off, makes the q walk from one side to the other. Yes, the proof of that, maybe I should just also once write down what is regularly varying, just that you see. Limit for r to infinity, well, y to infinity of f of x, y, x stupid, lambda over f of y is lambda to the rho. For lambda positive. So you see, if f of x were the power x to the rho, then that would be just trivial equality. Yes, and one calls a function with that property regularly varying with index rho, and to be that means to be, well, behaving almost like a power. Yes. For rho equal to infinity, one can formally do the same and so on, but never mind. Yes, so this is the definition of regular variation in Karamata sense, and it means to be nearly like such a power. And that's what I mean. The proof of theorem A is now completely different. Yes, it's completely different. It is the proof of theorem A. I think that the proof of theorem A is it now what really shows you why that intuition up there, why this intuition is not an intuition but a precise mathematical fact. Because it simply depends on a group action. You have the non-negative reals, and you have the set of all Hamiltonians, a set of all such, let me denote it like double H. Yes, and then you have a map. If you have R, non-negative number, and you have a Hamiltonian, then you map it to a Hamiltonian which let me call it ARH. Rescaling, and what is ARH? It is a Hamiltonian, and namely it is defined by rescaling. Yes? So what does this mean? You have H, let's say here is 1, and then you rescale. What happens? If R is very large, what does it mean? When R is large, then at the point R, I have what formerly was 1. Yes? Yes, of course. If I put R here, then I get 1. Yeah? So what this does, when R is large, let's say, it blows up. Yeah? So it makes what it makes the vicinity of 0 really visible, really big. Yeah, that's what this rescale, I mean, and this is a continuous group action if you put proper topologies and so on and so on. Yeah? And the crucial thing is now that the Weyl functions are related as follows. The Weyl function of such a rescaling at the point Z is the Weyl function of the original one at the point R times Z, just by primitive computation. Well, Z, let me put I. Yes, and suddenly here we can translate between behavior of that one fixed Weyl function towards I infinity and behavior of a family of Weyl functions at a single point. Yes? And this interplay, moving from that side to the other and vice versa, you can use in order to establish the theorem A. And this now really shows the intuition perfectly well, because you see, large points up there correspond to large rescaling. What is large rescaling? Blow up the vicinity of 0 and make it the important thing. Yeah, so it is clear that that behavior corresponds to that behavior, kind of. Okay, I think that the time is done, and yeah, thank you for your attention.
Thank you very much.